Okay, we start with one example. Example from the base excitation. We have a structure consists of a mass and two base with an equivalent stiffness K over 2, which K is about 0.1 meganewton per meter. The mass of the structure is 2000 kilogram, and this system is subjected to a base excitation. The acceleration of the base is 100 sine omega t, which omega is the frequency of the excitation, and it's equal to 25 radian per second. Also, we have the initial condition for the base excitation and also for the structure, which is equal to 0. So all of the initial conditions for the structure and for the base excitation are 0. And also we have the acceleration. So from the initial condition of the base excitation and also the equation for the acceleration, we can extract the displacement of the base or the base excitation displacements. So we want to find the horizontal displacement of the flow. So the purpose of this example is to obtain this xt as a function of time and of the building frame shown below when the ground acceleration is given. So we have this ground acceleration. So we deal with a non-homogeneous equation. Because the initial condition is 0, we can neglect the homogeneous response, and only it will be the particular response which will affect on the motion of this system. So we have the acceleration, which is 100 sine 25 t, and also we can find the displacement of the base by integrating 2 times integrating the acceleration. So xg will be equal to, we will have two constants when you are calculating the integral of x double dot or the acceleration. We will have two constant coefficients, c1 and c2, because we have two integral. So we will have two constants. The first integral of x double dot is minus 100 divided by 25 times by cosine 25t plus c1, and the second integral will be minus 100 divided by 25 squared times by sine 25t plus c1t plus c2. So the c1 will be created in the first integral when you are calculating the velocity, and the second constant c2 will be created in the second integral c2 when you are calculating xg. And now we can use the initial condition for xg, which at t is equal to 0, the displacement and velocity, both of them are 0. So when you substitute into the xg, you can conclude that both two constants c1 and c2 are equal to 0. And finally, we can conclude that the displacement of the base is minus 100 divided by 25 squared times by sine 25t. This is the base excitation. Now we can extract the equation of motion for this system. This is similar to a simple single degree of freedom system with one mass and one spring with the stiffness K. So the equation of motion is mx double dot plus k times by x minus xg, because if we assume that here instead of these two base, we substitute one equivalent spring, the displacement of this spring is the difference between the displacement of these two h's, which is the difference between xg and xt. So we can write the equation of motion in this form, and by simplifying this equation, we can extract the non-homogeneous form of the equation of motion in terms of x. We will have mx double dot plus kx, which is equal to this term, and this is k times by xg, in fact. So here, this is 100 millimeter. We should convert it into meters, so it should multiply by 10 to the power of minus 3, or it should divide it by 1000. And also we have the k, which is the stiffness of the system and its given data, and it's equal to 0.1 times by 10 to the power of 6, because this is 0.1 mega Newton per meter. So we can substitute and simplify, and the non-homogeneous term will be 16 times by sine 25t. So the equation of motion is mx double dot plus kx is equal to 16 sine 25t. So we have one non-homogeneous ordinary differential equation. The non-homogeneous term is a sine function, is a harmonic with frequency 25 radian per second. So we can find the response of this excitation as a particular response for this equation by considering the particular solution as a combination of sine and cosine with the frequency of 25 radian per second. So you can see the equation of motion for this system subjected to the base motion is exactly similar to the equation of motion of a STOF system subjected to a harmonic excitation, or harmonic external force. From in terms of the mathematical point of view, the equation has the same form and the solution procedure is the same. So as I told you, you can consider that xp, or the particular response, is equal to the combination of sine and cosine function with the frequency of 25, because the frequency of the non-homogeneous term is 25. So we can assume that the particular response will have the same frequency. So xpt is equal to a sine 25t plus b cosine 25t, which these two constants will be obtained from the from substituting into the main equation. So we need to substitute into the main equation, which is this equation, mx double dot plus kx. X is a sine 25t plus b cosine 25t, and also we need x double dot. For this purpose, we need to calculate the second derivative of xpt. The second derivative of this function is in fact frequency squared times by minus times by the x, because this is a harmonic function. You know that the acceleration of a harmonic displacement is minus omega squared times by the displacement. So here xp double dot is equal to minus 25 squared times by xpt, which is a sine 25t plus b cosine 25t. This is the same as xp. So we can substitute xp double dot and xp into the main equation and collect the equations in terms of sine and cosine functions, and then by using the coefficients of sine and cosine functions, we can form two algebraic equations with two unknowns a and b, and by solving these two equations we can obtain a and b, and also we can obtain in fact the particular solution or the steady state solution for this system. So this is the equation of motion. This is the xpt, and this is the x double dot pt, and we can substitute. We will have m times by xp double dot, which is minus 25. Here you can see m times by minus 25 squared times by xpt plus k times by xpt. It must be equal to the non-homogeneous term, which is 16 sine 25t. This is the non-homogeneous term. Now we need to collect for cosine and sine function. In the left hand side, we will have, if you look at to this equation, and if you want to collect for cosine and sine, the coefficient of sine 25t, we will have minus m times by 25 squared times by a, and also we have another sine function which is k times by a. So this is the coefficient of sine 25t, and for the term cosine 25t, we will have minus b times by m 25 squared, and here we have another cosine which is b times by k, and this is the cosine term. In the right hand side, we only have 16 times by sine 25t. The coefficient of sine term must be equal, in the left hand side must be equal to the coefficient of sine in the right hand side of the equation. So this term must be equal to 16, and the coefficient of cosine, which is b times by this term, must be equal to the coefficient of cosine in the right hand side, which is 0. Here you can see there is no cosine, so it means 0 times by cosine 25t. So we can conclude that the coefficient of cosine in the left hand side must be equal to 0. From the first equation, we can, this is the first equation, we can conclude that a is equal to this value if you substitute the k and m from the given data. And from the second equation, you can see that b multiplied by this parenthesis must be equal to 0. This parenthesis is not 0 because k and m, if you substitute, will have some numerical value. And b multiplied by this number is equal to 0. It means that b is equal to 0. Now we can substitute into the response, and you will see that xpt, this term is 0 because b is 0. xpt is equal to a times by sine 25t, and this is the response of your system, or the steady state response of the structure subjected to the base excitation in the form of sine 25t. Any question? Is it clear?
Yes, sir. Clear, sir.
Okay. The next example, we have a uniform bar of mass m, which is pivoted at point O and supported at the ends by two springs as shown below. And P of a spring PQ is subjected to a sinusoidal displacement xt, which is x naught sine omega t. Find the steady state angular displacement of the bar when L is equal to 1 meter. L is the length of this bar. K is 1000 Newton per meter, the stiffness of the spring. The mass of the bar is 10 kilogram. X naught, which is the amplitude of the displacement for point P, is 1 centimeter. And omega, the frequency of the motion for point P, is 10 radian per second. So in this problem, we need to extract first the equation of motion. We need to obtain the stiffness, mass, and of course here we don't have damping. We need to obtain the stiffness and mass equivalent, and then we can obtain the equation of motion and solve this equation of motion. Here we can assume that the displacement of point Q is xq and the displacement of point P, which is xt. So we can conclude that the displacement or the elongation or reduction in the length of the spring PQ is equal to xq minus xt or xt minus xq. And we can find the force in this spring, which is equal to the F and it's equal to K, the stiffness of the spring, multiplied by the deflection, which is xq minus xt, or xt minus xq. It depends on the direction of the force. But for this force, this spring, the left spring, because one edge is fixed, the deflection in the spring is only the displacement of this point, which is equal to L over 4 times by theta, and theta is the degree of freedom, the rotational degree of freedom for this bar. And we can find the force in this spring, in the left spring, and it's equal to K times by the displacement of this edge, which is L over 4 theta. And finally, the force is equal to K times by L times by theta divided by 4. This is the force in the spring. Now we can plot the free body diagram, and we can write the moment equation about point O and extract the equation of motion for this system. Okay, the displacement of point xq, this point, which we call it xq, is equal to the length of the arm, which is 3 times by L divided by 4 times by theta. This is the deflection of point Q, and the point P, which is the displacement for this point, is x naught sine omega t. So the force in the spring, as I told you, is equal to K times by xq minus xt. And you can find the force in this spring as a function of xt, and this xt will appear as a non-homogeneous term in your equation of motion, and you will see. So to extract the equation of motion for this bar, we write the moment equation, or we write the Newton's second law about point O. If you plot the free body diagram, and if you assume that this bar is rotating in theta direction, we will have one force here due to the spring PQ, and also we will have one force here due to this spring, the left spring. We have the weight, but because the weight of this bar will create some initial deflection in the springs, will be ignored. And also we have two reactions at point O, which when you write the moment equation about this point, these forces will not appear in the equation of motion. We only have two forces due to the springs. We don't have any damper, and we don't have any external force. So the moment about point O is equal to the mass moment of inertia about point O times by the angular acceleration. The mass moment inertia about point O is equal to the mass moment of inertia about the mass center, if we call it G, plus m times by d squared, which d is the distance between the mass center and point O. You know that for a uniform bar, the mass center located at the center of this bar. So the distance between point G and point O is equal to L divided by 4. And we can calculate the mass moment of inertia about this point. The moment about point O is equal to the moment due to this force, K times by L over 4 times by theta, multiplied by its arm, which the arm for this force is this length, and it's equal to L over 4 again. The moment due to the spring PQ is equal to the force into this spring multiplied by its arm, which is 3L over 4. The force in this spring, as I told you, is K times by xq minus xt, and xq is 3L over 4 times by theta, and multiply by its arm, which the arm for this force is this length, and it's equal to again 3L over 4. So this is the moment about point O, and all of them have a negative sign, as you can see, because the moment due to this force, according to the assumption for the direction, the moment will be in negative direction of theta. So we consider one negative sign for the moments due to these forces. And finally, it must be equal to I O theta double dot. Now we can substitute for xt and simplify this equation and extract the equation of motion for this system. The equation of motion will be finally in this form, and then we can substitute the numerical value and simplify for the L and K. And also we can substitute the xt, which is x naught sine omega t, and extract the equation of motion in this form. This is the equation of motion, which is a single degree of freedom system. So the equation of motion is an ODE from order 2. We don't have theta dot because there is no damper in the system. We only have I O theta double dot times by the uh, equivalent stiffness. This is the equivalent stiffness for your structure, multiplied by theta, and this is the non-homogeneous term. As you can see, x naught sine omega t, this term is the displacement xt for point P, and this is appeared as the non-homogeneous term in our equation of motion. Now we need to solve this equation of motion by using the theory of ODEs. To solve this equation, we need to find a steady state or particular response. For this purpose, we don't need to form the characteristic equation and find the roots because we only want to obtain the steady state response. Please remember, all the time in the exam, you should pay attention to the problem description. Sometimes the problem asks you for the homogeneous response or transient solution. So you need to obtain the characteristic equation, find the roots of the characteristic equation, and finally find the homogeneous response. But sometimes the problem asks you the steady state or particular response. For this purpose, you need to obtain the particular response according to the form of the non-homogeneous term, and then find the constant coefficient by substituting into the main equation. Here we have a sine function in the non-homogeneous term with frequency omega. So the particular response is a combination of sine and cosine with frequency omega. So we consider A sine omega t plus B cosine omega t, and omega is the frequency of non-homogeneous term. Here you can see this is the frequency. Sorry. This is the frequency of non-homogeneous term. The next step, we need to substitute the theta p or the particular response into the main equation to obtain A and B, similar to the previous example. So we need to obtain theta double dot. When you want to substitute into the main equation, we need the form of theta double dot and theta. Theta double dot, here we have a harmonic function. So theta double dot is equal to minus omega squared times by theta. And then we can substitute into the main equation. We will have IO, or the mass moment of inertia, multiplied by theta double dot, which is minus omega squared times by theta p, plus 5 over 8 times by KL squared. This is the equivalent stiffness, multiplied by theta, which is A sine omega t plus B cosine omega t, and it must be equal to the non-homogeneous term. Again, we will have two algebraic equations. One is the coefficient of sine functions, sine terms, and the second equation is due to the coefficients of cosine terms. The sine terms in the left hand side, we will have minus I O omega squared times by A, and also we have the equivalent stiffness 5 over 8 KL squared times by A. It must be equal to the coefficient of sine, which is 3 over 4 KL x naught. So this is the first equation. The second equation is the coefficient of cosine, which is B times by minus I O omega squared. We we have another cosine term here, b times by 5 times by k, L squared divided by 8. It must be equal to the cosine coefficient in the right hand side, which is again 0. So this is the second equation. From the first equation, we can find A, and from the second equation, we conclude that B is equal to 0. Any question? Is it clear?
clear, sir.
Okay. The next concept in this chapter is the response of a damped system under rotating unbalance. We should note that one of the most important reasons of vibration in the machines, especially when we deal with a machine with rotating parts like electrical motors, or in a car, for example, in the tire of a car, and in the engine, in the crankshaft, in the gearbox, in the shafts of the gearbox. Most of the time when we deal with a rotating component in our machine or in our structure, we deal with an unbalancing, and the unbalancing is the reason of the vibration in our structure. For example, here in this course, we only discuss and investigate the effect of unbalancing on the motion of a very simplified structure, STOF structure. Here you can see we have a system with total mass M, with total mass uppercase M, of course. The stiffness of the structure is K, so it means that we have one spring with stiffness K, or two spring with stiffness half K. We have a damping with coefficient C. We assume that the unbalanced rotating has a mass of lowercase m divided by 2. This is the mass of the unbalancing, and we have two unbalanced particles which are rotating in opposite direction. We assume that they have opposite direction because when we have the opposite direction, the horizontal components will cancel out the effect of each other, and only we will have the vertical components. If we neglect the horizontal component, we deal with an only single degree of freedom system. But if we consider the effect of horizontal components, so we will have another motion in horizontal direction, and system will be a 2 degree of freedom system. So in this chapter and in this course, we only consider the effect of a vertical motion, and you will see the effect of this motion on your equation of motion and on your response. So this is the general form of the unbalanced rotating. Because these two particles are rotating about this point. As you can see, this one is rotating in counterclockwise direction, and this particle is rotating in clockwise direction. So due to the centrifugal acceleration and centrifugal force, we will have two components in horizontal and vertical direction. The horizontal components are mass times by the radius times by omega squared, which omega is the angular velocity, multiplied by cosine omega t, which omega t is the uh, angle between the centrifugal force and horizontal direction. For the second mass, we have exactly the same horizontal component, but with the opposite direction. So these two forces will cancel out each other, but the vertical components in vertical direction, both of them will have the same direction. So we only have one force in vertical direction. For example, in this moment, it will be in downward direction, and it's equal to m times by the radius times by omega squared, which radius of the unbalanced particle is called E, lowercase e, as you can see here. So the vertical force is me omega squared. We have two mass with mass m divided by 2. So the summation of these two mass is equal to m times by e times by omega squared. And omega is the angular velocity. So you can see we can have different conditions. For example, these two omega can be different, or the direction of omega will be both of them in the same direction. For these cases, we will have a system with more than one single degree of freedom, because the system with mass uppercase m, this system can have an horizontal motion in addition to the vertical motion. Here we assume that the vertical motion is xt, but if you consider different cases, we will have another motion in horizontal direction, and for example we can call it yt. So you will deal with a system with 2 degree of freedoms, but here in this case and in this chapter we only discuss single degree of freedom systems. So let's extract the equation of motion for this system subjected to two unbalanced rotating masses. If you extract the equation of motion for this system, you can see this is mx double dot plus cx dot plus kx, which this m is the mass of the system, the mass of the structure. It's not the lowercase m. And you can see these two lowercase unbalanced mass m, these are the unbalanced masses. And it's very important to know that these masses are not considered in your system's mass, and they are appeared here in the right hand side of the equation as a non-homogeneous term, and their effect is similar to an external force or a base excitation. So the effect of these unbalanced masses are similar to the external forces or base excitations, and will affect as a non-homogeneous term on your equation of motion, and they will not appear into your mass of system. Into your equation of motion, you can see that the coefficient of the acceleration, which is the equivalent mass, is exactly the mass of the structure, and the coefficient of x dot, which is the coefficient of damping, and the coefficient of x, which is the stiffness of the structure. Now we have an ODE from order 2 with non-homogeneous term, and we need to obtain the particular solution for this structure, or the non-homogeneous solution. The homogeneous solution for this equation is easy. It's exactly the answer of an STOF system, and you can easily find it. But here we need to obtain the particular response, and the particular response for this structure is, because here the frequency of the excitation is omega, it will be a particular response with the frequency of omega. And also we will need to obtain the amplitude and the angle phase. Also, you can consider that xpt is a combination of sine and cosine functions with frequency omega. I mean, you can assume that xpt is equal to, for example, a times by sine omega t plus b times by cosine omega t. So this is again xpt, no different. You can consider the particular response in this form and then obtain a and b. But here we assume that xpt is in only sine function, because in the next slide you will see that we want to discuss the effect of the unbalancing on the response of the system. So the amplitude of the response is equal to this value. As you can see, this is a function of m, which is the mass of unbalanced particle, a function of e, which is the radius of the unbalance, and omega, which is the frequency of rotation. and also K, M, and C are appeared in the denominator of the response, which are affect as the characteristic of your system on your amplitude of the steady-state response. And finally, the angle phase, again, if the damping coefficient was 0, so angle phase was 0. As you can see, this is directly depends on the coefficient of damping in your system. If we define the damping ratio and use from the previous definition, C divided by 2m times by omega n, which omega n is the coefficient of x divided by coefficient m, of course a square root of this coefficient of x divided by coefficient x double dot, and then we can find this parameter, which is the unbalancing displacement, the ratio of m times by x divided by me, which is a function of r, frequency ratio, and psi, which is damping ratio. And also phi again can be rewritten in this form as a function of damping ratio and frequency ratio r and psi. So r is omega divided by omega n, or the ratio of frequency of the unbalanced motion to the natural frequency of your system. We can now discuss the effect of the frequency ratio and damping ratio on the rotating unbalance. Here you can see, if you plot the graphs for mx divided by me, which is called rotating unbalance, all of the curves will start from this point 0. What does it mean? It means that this force is due to the motion of the mass with lowercase m mass, or unbalanced mass. So if this mass didn't have any rotation, or if this mass was at rest, there is no force in the system, and the particular solution or the steady state solution will be 0. So all of them start from 0 when omega is 0. This is the first conclusion. The amplitude here in this area, when we are close to the resonance, or when we are close to the R is equal to 1, it's significantly affected by the damping ratio psi. As you can see, the effect of psi on your response is really significant. And usually in all of the systems with all different types of excitation, it can be external force, harmonic, periodic, non-periodic, or any other types of excitation, or base excitation. And even here in the unbalancing systems, the most important effect of damping will be appear in around the resonance. And in fact, we use the damping to control the motion, to control the vibration around the resonance, and to prevent the resonance in our structure. The next one, at very high speed of omega, here in this area, you can see that the rotating unbalance is almost unity. In fact, when the frequency of the unbalanced motion increases, it will affect as a static force on your system. So when the frequency of the rotation increases, you can see that the effect of the unbalanced force is like a static force. And you, after a while, you will see that the vibration motion will vanish, and we don't have any vibrating motion. And only we will have an deflection in the structure. For example, if we assume an electrical motor, by increasing the speed of the rotor, you will see after a while the motor will be stable, and it will be at rest, and all of the vibration will vanish after a while by increasing the frequency of rotation. And the next one, for psi between 0 and 1 over square root of 2, we can achieve a maximum value for the rotating unbalance and it's equal to this value. Again, it's a function of damping ratio, and you can see that it's not a function of frequency ratio. Of course, it must be equal to this value. For a specific value of R, we can achieve to the maximum value for the rotating unbalance. And the two last conclusions, which are clear: when damping ratio is more than 1 over square root of 2, we don't have any maximum. For example, here you can see we cannot attain a maximum value for the rotating unbalance. So again, you can control your motion by using the damping, and you can see by changing the psi and increasing, in fact, increasing the damping coefficient or damping ratio, you can decrease the rotating unbalance, and you can vanish the maximum value for your rotating unbalance. And finally, the force transmitted to the foundation due to the rotating unbalance force is Kx plus Cx dot, which this X, in fact, is the response of your system, and it's similar to the force transmitted in to the base excitation. Okay, any question from this part? If you don't have any question, we can wrap up this session and continue again tomorrow.
No questions, sir.
Okay, thank you. So we can continue with some examples tomorrow, and we can wrap up this chapter by tomorrow. Thank you for your attention, and see you again on tomorrow. Bye.